from current slide. And you've heard both of the announcements before, I think. The volleyball team will be participating in the NJCAA, which I assume stands for National Junior College Athletic Association, District L/M tournament. Now, I don't know if we're down in District L and M or whatever this is, or if that means ladies and men, I don't know, but it's going to be up in Boaz, Alabama, which is where Snead State Community College is, and I assume it's on their campus. And then the other was the announcement about the one-week summer opportunity for college students that are interested in a biopharma manufacturing careers. They will pay you $1,000 and travel expenses to go for that 1 week. So they must really be hungry for people interested. It sounds like quite a good deal. So I bet you it would be nice. Any questions on anything we've done so far? Okay. Well, we're in Chapter 13, which is Functions of Several Variables, which is, to me, the most important chapter in this course is functions of several variables and doing partials and things like that, and then all the applications of that. And the next one is then integration, multiple integration. So those two, to me, are the core for Cal 3. And the other stuff that we've done is all good stuff, too, but these are the core ones. And so we're on page, we're in section 13.6, directional derivatives and gradients. And the topic that's on page 927, functions of three variables. We've been dealing with two independent variables. Now we're going to go to three. Now, hang up trying to graph these, because that would be the dependent variable would be in the fourth dimension, and I don't know how to go there. Okay. And it seems like to be I think it's something to do with this plug here. I think when it gets hot, the power fluctuates, because I don't know if this is showing it, but my computer is just, well, it's now sort of flicking in and out a lot. But anyway, functions of three variables. And here are the verbiage that sums all this up. Directional derivatives and the gradient for three independent variables. Let F be a function of three independent variables, x, y, and z, or any other three you happen to choose, with continuous first partial derivatives. F has to have continuous first partial derivatives. The directional derivative of F in the direction of a unit vector, u is equal to ai plus bj plus ck. Of course, that would be a unit vector. That means, of course, a, b, and c. Unless two of them are 0, they all have to be less than 1. Okay? So that unit vector is given by, should look very familiar, the directional derivative in the direction of that unit vector v of the function f of x, y, z. Now, this is a scalar function here, and you're taking a directional derivative in that scalar function, of the scalar function, in the direction of the vector, u, unit vector u. Now, think the u vector dotted with the gradient vector. We're getting there. It will be somewhere, well, I guess they ever say it. That's exactly what you're doing. A from here times the gradient of f is the partial of f with respect to x, y, z. With respect to x of x, y, z, that would be your gradient vector in the I, component in the I direction would be this, then that's your u in the I direction. So the dot product goes to the A times f sub x plus b times f sub y of x, y, z plus c times f of z of x, y, z. So the directional derivative in the direction of some unit vector u, sorry, I can hardly talk, would be the dot product of that unit vector with the gradient for this function. Okay. The gradient is defined as, I've already been using it as if they've already defined it, grad or gradient or del f of x, y, z, partial of f with respect to x, y, z, I, plus partial of f with respect to y of x, y, z, j, plus partial of f with respect to z, x, y, z, k. Okay? Now, just like we did the partial in 2 dimensions, okay? Or the gradient in 2 dimensions. Properties of the gradient are as follows. This that we just said here is the gradient dotted with the u, or u dotted with the gradient. It doesn't matter which way you said. That's how I said to remember that. It's the easy way to remember. Now, if this gradient function is equal to 0, the gradient is equal to 0, then since the directional derivative of f in the direction of u is the dot product of the gradient with u, then this directional derivative must be 0 for all values of u, for any u you happen to choose. Okay? So if you're at that peak, whatever that is, whatever is happening up there, that your gradient is 0, then your directional derivative is 0 no matter what direction you put it in. Okay? The direction of maximum increase of f is given by your gradient. And if that's 0, you have no point of maximum increase. You're flat. You can't go up or down. The maximum value of this du, the directional derivative of u, in the directional derivative of f in the direction of unit vector u would then be the direction of maximum increase is given by the gradient vector, and the maximum value of that would be the magnitude of the gradient vector. The direction of minimum increase of f is the negative of that gradient vector. That would be in the opposite direction, and the minimum value would then be the negative of whatever that maximum value is. Okay. That's of the directional derivative of f in the direction of the unit vector u. I think that sets us up. I'll let you write that for example 8. Now, I think just about all this is directly just an extension of what we have for 2 dimensions. So, the gradient of f is that is in the direction of maximum increase. You dot that with u, and that gives you the directional derivative of the function at that point. Okay. Got it? Okay. Here's example 8. Find del f, or grad f, gradient of f, x, y, z for this function. X squared plus y squared minus 4z, and find the direction of the maximum increase of f at the point 2, -1, 1. Okay? So let's do what they say first. Let me get my pen set up. Find the gradient of f. Yep. That would be 2x. That's in the I direction. This is a vector, right? Plus 2y
Okay, my pen's screwing up on me. Okay, 2y in the j direction, minus 4 in the k direction. Got it. Okay, there's your gradient. Now, find the direction of maximum increase of f at this point, 2, -1, 1. So that's going to be the gradient of f at 2, -1, 1. So where would that be? 4i minus 2j minus 4k. Okay, 1 there doesn't come into play at all because that. Now, it says find the direction of maximum increase. That is the vector in the direction of maximum increase. Quite often, when they say the direction, they mean what direction is the unit vector pointing. And so they sometimes will take that down. No, they're not going to do it. They just plug it in. That's all they do. Yeah, that's all they do. Okay, and that's it. I thought there was going to be something more to the problem, but that's not it. The direction of maximum decrease would then be the exact opposite of that. Would be at this point would be minus 4i plus 2j plus 4k. They didn't ask for that. They didn't ask for what would be the magnitude of the maximum increase. Okay. Now, done what they said. They're going to follow it with a picture. So I'm looking forward to looking at the picture.
Can we assume on the point of the unit vector, the vector pointing to the direction unit vector, if you just leave it positive, it's always considered positive. But the moment you change the sign, then it's pointing the opposite way.
Right. Yeah. Yeah.
So we don't have to work every time we say find the direction. Just don't mess with the unit vector.
Right.
Just leave it the way it is, and it'll always point in the direction of the unit vector.
Yeah. Okay, wait. You mean the gradient is...
Yeah. They say, okay, find the direction.
Right. Direction of maximum increase is what the gradient tells you.
Okay.
This isn't a unit vector.
But in the direction of the unit vector.
Yeah. I was saying that. I thought they were going to ask for that as direction of the unit vector, but it's the same direction as this, but quite often when they say a direction, they will list a unit vector. They didn't in this case. They just listed it, which that gives a direction. It definitely does. Now, let me go on and erase this. Okay, so you can see how it is. The gradient of this is just, like you said, the partial with respect to x of x, y, z in the I direction, partial of f with respect to y in the x, y, z direction, in the j direction, partial of f with respect to y of x, y, z in the j direction, plus the partial of z as a function of x, y, z in the k direction. That's what the gradient is. Okay, partial one, each in this direction. Okay, so taking that partial is 2x I plus 2yj minus 4k, exactly like you did. And then if you plug it into the point, 2, -1, 1, then that would be 4i minus 2j minus 4k, just like you did. Now, there's something about this. Oh, okay, I got what it is. Of course, we can't see, what I said earlier. You can't draw a four-dimensional graph, okay? So this is a level surface of that four-dimensional whatever it is, okay? Whatever your fourth dimension is, you plug in that to this formula, and that would give you whatever that fourth variable would be, W or whatever, okay? Now, if you do what they call a level surface, all the values at which the gradient is equal is the same here, and then at this point, the gradient is going to be perpendicular to that level surface. Just like it's perpendicular to a level curve, in 3 dimensions, it's perpendicular to the level surface. So this is perpendicular to the X direction, Y direction, and Z direction. This is perpendicular. The vector is perpendicular to that. And that would be 4 I, so it's coming out here on the I, 1, 2, 3, 4. Okay, but of course it's translated from here to there. Minus 2J. So this is pointing back this way. It's hard to see that it is. And of course it's pretty obvious it's pointing in the minus Z direction too. But it's just not so obvious that it's pointing in the minus Y direction. In fact, that doesn't look like it is. Okay, I don't see that at all here. It seems like that thing should be pointing back more this way. But, and it also seems like that would be more perpendicular to that surface at that point. But I can't argue with their graphics because I can't do that well. Okay.
Now the 4K is in the direction of Z.
What's that again?
The 4K, the minus
Yeah.
4K. Well, since
yeah.
okay, there's the 4. Oh, I see. The 4K is down there.
Yeah. And what that is indicating to me is that your no matter where you are on this, you've got a minus 4K component to it. You know, and they can be quite long here or short or whatever, but it's always minus 4K. At the tip down here, that's minus 4K, you know, and 0x, 0y. And out here, but it always has that component downward of minus 4K. Various x's and y's, you know, but the z component of that gradient vector is always negative 4K. Z component minus 4K. Which is sort of interesting, and I think that's what makes the level surface a paraboloid. You know, is that, remember, a parabolic mirror always sends light, receives or sends light in the parallel direction. Yeah, exactly. And so this is the Z component here would then be on the inside of that. It would be what, just the opposite, 4K, a plus 4K everywhere there. All right, and that was example 8, and that was the last example in 13.6. So homework exercises here include 3 or 5. They're both at Calc Chat. 3's at Calc View. 7 or 9, they're both at Calc Chat. 7's at Calc View. 11 or 13, they're both at Calc Chat. 15 or any of the odds 15 to 19, they're all at Calc Chat. 17's at Calc View. 21 or 23, both at Calc Chat. 25 or 27, both at Calc Chat. 25's at Calc View. Any of the odds 29 to 37, they're all at Calc Chat. 31's at Calc View. 39 or 41, both at Calc Chat. 41's at Calc View. 43 or 45, both at Calc Chat. And then 47, I think I'd do 47. It should be at Calc Chat. Multiple parts of it. And then there's an investigation at 49. If you want to follow that, you can. That should be at Calc Chat. 51s, you can think about doing that. It should be at Calc Chat, and there's a topography problem, 53, and it should be at Calc Chat. Oh, more. 53 is topography, 55 is temperature, so pick one or the other of both of those. 57 should be at Calc Chat. It's also at Calc View. 59 should be at Calc Chat. It's also at Calc View. And then either 61 or 63 should both, they're true-false questions, they should both be at Calc Chat. And then it says find the function. They give you some information and they want you to find what function gives you that as a gradient. Okay, so you're sort of undoing the gradient. 67 is using a function. 65 is finding one. 67 is using one. Okay, I think that probably is the last slide. It is. So let's close this out and move on to 13.7. Goodness gracious. By Wednesday, I'm just running out of energy. Of course, I had a doctor's appointment yesterday. That took a bit out, but not too bad. All right, let's go from current slide. Still in Chapter 13, functions of several variables. 13.7 is tangent planes and normal lines. Now, if you think about with two-dimensional situation, a tangent line to any point on the curve, and then the normal would be perpendicular to that tangent line. Now we're moving into three-dimensional objects, and rather than having a tangent line, they do have, but they have an infinite number of tangent lines at any point, and they define your tangent plane. But there's still only one normal line, because this tangent plane, all those have the same normal line. The line is perpendicular to all those tangent lines in the tangent plane. All right, the objectives here, we'll find the equations of the tangent planes and the normal lines to surfaces. We'll find the angle of inclination of a plane in space. Sort of an interesting concept there. And we'll compare the gradients, del f, or the gradient of f as a function of xy, when your function f of xy is equal to something, okay? And you rewrite that as capital F of xy, okay, rephrase that. Say that your function f of xy is equal to z, okay? That could be your shape, the quadrant surfaces we did, or anything else, you know, some function of x and y is equal to z. Then that's your little f, and we'll look at that gradient and see how that compares with the gradient when you take that z, move it on the same side with your x's and y, and that makes a new function, capital F, okay? And then what will its gradient look like when you do that type of maneuver to it? Okay, we'll compare those gradients. So let's start with the tangent plane. When you have a surface, you have a tangent plane to that surface, whatever that plane is, you know, and then the one and only one normal line to that surface. All right, you've represented the surfaces in space primarily by equations of the form z is equal to f of xy. This could be quadrant surfaces or any surface, okay? Z is equal to some function of x and y. There are xy planes down here, and z is defined for every point over that plane. And the development to follow, however, is convenient to use a more general representation. This is what I was talking about. Take the f of xy, whatever it is, subtract z from it. That gives you a new function, capital F of xy and z. Now it's a three somewhat independent variables, and that function's always got to be equal to 0.
In fact, we've done a little bit of that kind of stuff in differential equations. We have this first. Okay. For a surface S given by z is equal to f of xy, one we were talking about before, you can convert the general form by redefining capital F as little f minus z. Subtract z from both sides. That makes this equal to 0. That gives you your capital F of xy and z. But you know in your heart of hearts, z is a function of x and y, so it doesn't quite feel like it's a completely independent variable. And that's, of course, because the c, you might say, is always equal to 0. Okay. Because f of xy minus z is equal to 0, you can consider s to be the level, that's what I was saying, I called it c, but s to be the level surface of f given by this, okay? And that's the only surface you're really interested in, is that. The alternative equation for the surface S, which would be z is equal to that, is f of x by c is equal to 0. So, here's a function. F of x, y, z, and this one, I think you have to say z is completely independent. Okay? This is not one that you have a little f that you can solve for uniquely, because it'd be a plus or a minus at best. Okay? So this is one that the z appears to be completely independent of that. Okay? For this function, capital F of x, y, z is equal to x squared plus y squared plus z squared minus 4. Describe the level surface given by f of x, y, z is equal to 0. So in other words, what happens, let me get my pen back, when this is equal to 0. That function is equal to 0. Describe that level surface. What would be that surface?
I would think that that's the, look at those powers. I would think that's the bowl.
A ball, a sphere of radius 2. You're absolutely right, because all you have to do here is add 4 to both sides here, and you get x squared plus y squared plus z squared is equal to r squared. Sphere of radius 2, centered at the origin even, okay, of radius 2, okay? That's the level surface given by that formula there. That's equal to 0. That's the surface you're on. That's all you got, okay? Right there. So the level surface is that. You can rewrite that. Add 4 to both sides. That's the sphere of radius 2 whose center is at the origin. Exactly right. Now, normal lines are equally important in analyzing surfaces in solids. For example, consider the collision of 2 billiard balls, okay? When a stationary ball is struck at a point P on its surface, it moves along the line of impact determined by P and the center of the ball, okay? So, if you were to hit the cue ball against this one, and it hits at that point there, this ball has to take off in that same direction you were going there. Okay? I never can get to do that, but they say it will. Okay. It's supposed to work that way. Okay. Now, if you were to hit the cue ball at a glancing blow, wherever it touches here, that's the direction this ball takes off to. Theoretically. Okay?
I know this is something.
Yeah, it seems like they always end up scratching to me, but I don't know. This one goes in the pocket, that one doesn't. Okay. But anyway, if you hit it dead on, it's going to go supposedly in that direction. When the cue ball is not moving along the line of impact, that's what I was just saying, at an angle, it's deflected to one side or the other and retains part of its momentum. Okay. Let's go back to here. What they didn't say here, well, they did, okay? Yeah, it does. I didn't read it. When the cue ball, okay, sorry. I think I skipped this one, okay? I read this and went right to here. The impact can occur in two ways. When the cue ball is moving along the line of impact, yeah, okay, it stops dead. Nothing to do with Josh coming in, okay? And you look ready for winter.
It is
Okay.
wet outside.
It is nasty. Okay. All right, we're in we're still at chapter 13, which is functions of several variables. We just started section 13.7, tangent planes and normal lines. We're playing pool. We've been playing while you were gone. Okay. All right. So you hit a stationary ball, 3-ball in this case, is struck at a point P on its surface. It moves along the line of impact determined by P and the center of the ball. So that line of impact, where that is, and the center of the ball moves that way. So that impact can occur in two ways. I skipped this paragraph. When the cue ball is moving along that line of impact, then the cue ball supposedly stops dead and imparts all of its momentum to the stationary ball in this way. So the cue ball is supposed to stop and the stationary ball take off, supposedly at the same velocity as the cue ball had coming in. Now, places where this kind of messes up, okay, number one. How about I heard somewhere the cue ball is just slightly heavier than the other balls. So the momentum will be equal, but that meant this one would be going a little bit faster than the cue ball did. Okay? Except, of course, you lose a little energy with friction and sound and stuff, so it's pretty close to the same. Now, the other issue here is that if you've hit the cue ball, even though you're going on a straight line, but hit it with a certain amount of spin on it, then it also has angular momentum. Angular momentum will keep it rolling or do something else to it. So it doesn't always stop completely dead. And it's not violating the law of conservation of linear momentum. It's just that it also has some angular momentum. But if it's scooting along the table or pretty close to scooting on the table, it should stop pretty close to a dead stop there. Okay. Supposedly. Okay. Now, when the cue ball is not moving along the line of impact, it's deflected to one side or another and retains part of its momentum. So when the cue ball comes in like this ball has to leave perpendicular to the line of impact. Well, if you think about it, this cue ball has a component of its momentum in this direction and another component in that direction. This ball leaves with the same component that the cue ball had in this direction. The cue ball then maintains its momentum in the direction along the line of impact, because it only has two components coming in, one along the line, one perpendicular to the line. When it hits this one, this leaves with the momentum perpendicular to the line, and the cue ball continues along the line, parallel to the line of impact. Okay. So the part of the momentum, part of momentum that is transferred to the stationary ball occurs along the line of impact, regardless of the direction of the cue ball, shown here, and the line of impact is called the normal line to the surface at point P. Now, I've seen these guys who are really, think of themselves as really good pool players. They'll go and line up on the number 3 ball and line up right in the direction of the pocket they're trying to hit it to, or the bumper, if they're trying to hit it on the bumper and bounce off. They'll do that, and then that's where they aim the cue ball. I never get it to hit there, but that's where they aim it, and then it should go straight into the pocket or straight into the buffer to go into the pocket. But the cue ball then is going to leave there because it's imparting all of its momentum perpendicular to that line, and it continues with whatever momentum has parallel to the line. Okay. They're not worrying about the cue ball, though they show it. They're worried about where it is. And this is called the normal line. The normal line to the point of impact. Okay. In the process of finding a normal line to a surface, you are also able to solve the problem of finding a tangent plane to the surface. All right? This takes us back to our planes and normal lines. Did we do that this term or last term? I think it was this term, early. Yeah, was it early this term? Yeah, you weren't here last term. Okay. Let S be a surface given by, now there's your capital F version, which is always equal to 0. F of x, y, z equals 0. And let this point P, which is at x0, y0, z0, be some point on that surface. Has to be on that surface. Okay? And let C be a curve on that surface through this point that is defined by the vector value function. So C is defined by a vector value function. R of t is equal to x of ti plus y of tj plus c of tk. Okay. Now, then for all values t, because this defines an x, y, and z for you at any value t, that's a curve on the surface. Has to be on this surface. P is on the surface. Then, if it's on the surface, then that has to be 0. So your x of t, which is your I component, y of t, which is okay, z of t. Every value t that's on that surface, then this thing has got to be equal to 0. Okay. So where are we going with this? If that capital F is differentiable and x prime, y prime, and z prime all exist, and I just can't imagine F being differentiable without them existing, but let's play that as another issue here. Then it follows from the chain rule that F prime of t is equal to 0. Now,
Question.
yeah.
In this case, R prime of t, aren't we looking for that to be 0 anyway?
This one right here?
No.
I thought you said R prime of t. Okay.
R prime. Yeah, R prime t 0.
Oh, down here. Down here. Okay, I'm sorry. R prime of t 0. Okay. I thought you said R prime is equal to 0. I said, okay, got it. Okay. R prime of t 0, what were you saying about it?
Isn't that going to be 0 anyway? Isn't that what we're going to look for?
Let's see how to say this better.
We set that equal to 0.
When we set it equal to 0, then you're at one of those.
Well,
It's a max-min type thing.
Yeah.
Yes.
Okay. Okay, so we just look at the vector now, not the, say if we have a surface down here, and we've got,
right,
say, a curve up here,
right,
we've got at the tip of that sort of point, say, so that's the max up there.
Right.
We are not looking for that in this case.
Not yet. That's where we're heading, right? I think that's where that's going to be an application of this, I believe. If I'm understanding what you're asking. What we're going to do is find those maxes and the mins and other strange surfaces. Okay. I think if that's what you're asking, yeah, that's where we're heading with this. Now, to me, this is sort of bizarre, because if you think back, f of t is equal to 0, right here. F of x, y, z is always equal to 0, no matter what your t is, okay? If you're on that surface, you're there, and the f is going to be 0. So f prime has got to be 0 too. Derivative of 0 is 0. So that's what they're saying here, which is not a very enlightening thing, but what they're saying is, break that down. What is f prime of t? Now this is change of f with change of t. That's what the prime is implying here. So what that is the change of f with respect to x times the change of x with respect to t. That's where the chain rule comes into play. I thought when I first read this hasn't got anything to do with the chain rule. That's the fact that the function 0 is derivative is 0. But the chain rule comes from this step, when you break down what this is, because the prime here indicates with respect to t. So the change of f with respect to t would be the change of f with respect to x times the change of x with respect to t, plus the change of f with respect to y times the change of y with respect to t, plus the change of f with respect to t times the change of z with respect to t. And we know this has to be equal to 0. I should have written it down here to enforce that's what you're doing. So if you're at this point, x0, y0, z0, the equivalent vector form of this is, this part here is your gradient of f, and this part here is your r prime. Okay? We didn't say r prime back here, but if you took the derivative of r with respect to z, that would be x prime of ti plus y prime of tj. Okay? So that's your r prime. Now that's what you were talking about then, right? At this point, that's your r prime at t0, where t0 is the value you would be when you're at x0, y0, z0. Okay. So, and this would be the gradient at that. Now, you have one of two possibilities here. Since this, you know, is equal to 0, this is either going to happen when your tangent vector is equal to 0, in other words, your speed is 0 at that point, or where the gradient is equal to 0, which means you're on a contour, okay? And you're heading in that direction, okay? So, either one of those will produce a product there equal to 0. Okay? That may be where they're heading next. I haven't flipped the page to see. Okay, so let's see where they do. Oh, I'll let you finish writing. Okay. Now, so where are they heading with that? This result means that the gradient at P is orthogonal to the tangent vector. Okay. Oh, here's the other corresponding thing with that. For the dot product to be 0, if this vector is not 0 and that vector is not 0, for the dot product to be 0, that means these two things have to be perpendicular. Because that's the only way you get a dot product to be 0, unless one of the other is 0. So I think we're assuming this is not 0. I think that was an assumption earlier, wasn't it? I'm not sure. Seems like they are going to bring that. And as long as the speed isn't 0, you're not at a place there, then it means that the gradient at P has to be orthogonal to the tangent vector at P. Okay? For every curve on S that goes through P. Okay? So all the tangent lines on S lie in a plane that is normal to the gradient vector. The gradient vector is the direction of maximum increase, and then your tangent plane is orthogonal to that. Every tangent vector is orthogonal to the gradient vector right there. Okay? Now it seems like to me they could say something right now that would be so much, to me, clearer. That gradient vector has to be your normal vector. Okay? Why haven't they said that? I don't know. But I guess they're trying to do the tangent plane first, and then they'll come around to that. Okay. So at some surface S, at some point x0, y0, z0, the place where, and this is your F vector here, it's equal to 0, and at some point where that's true, then at that point that's your normal, well, I would say this, that's your tangent plane, where all those are perpendicular to your gradient of F. Okay. So here's the definitions of the tangent plane and the normal line. Let F be differentiable at the point P of x0, y0, z0 on the surface given by this. F of x, y, z is equal to 0, such that the del F, here's what they say it. The del F, the gradient of F, at that point is not 0. Okay, if it was 0, then all this other stuff is out of there. Okay, you don't have a normal line there. Okay, the plane through, if you don't have a normal line, you don't have a plane. The plane through P, okay, that is normal to that is called the tangent plane to S at the point P. To that surface S at the point P. With this surface S. Okay? The line through P having the direction of the gradient of alpha x0, y0, z0 is called the normal line. Line through P in that direction. So that's why I said, why don't they only call that the normal vector? But they're talking about normal lines here, so that may be why. To find an equation for a tangent plane at x0, y0, z0, now, are they doing this on purpose? I don't think so. But it just seems like to me, maybe not, just seems like to me that Z was elevated a little bit, and it looks a little bit bolder, but maybe it's just an optical illusion. I don't know. Okay. To find an equation of the tangent plane at 2S at x, y, 0, y0, z0, let x, y, z be an arbitrary point on that tangent plane, somewhere out there, then the vector v, which is, this is the point on the plane, and that, of course, is the point where the plane touches the curve. So x minus x0i plus y minus y0j plus z minus z0k lies in that tangent plane. All those vectors that fit that bill lie in the tangent plane. Because the gradient of F at x0, y0, z0 is normal to the plane at x0, y0, z0, it must be orthogonal to every vector in the tangent plane. And then you would have that gradient vector at that point, dotted with this, has to be 0, which leads to the next theorem, equation of the tangent plane. If F is differentiable at F has to be differentiable at that point. This is the capital F, where it's equal to 0. Okay. Then an equation of the tangent plane to the surface given by this, that's the surface, at that point there is, here's the equation. Your partial of F with respect to x, this is the component of it, not the I. This is the value of that. Times x minus x0 plus the partial with respect to y at that point times y minus y0 plus the partial z with respect to that point z minus z0 is equal to 0 because of this. Now, remember this. You've taken the partial with respect to x of x0. Okay. You plugged in these values. So this is just a number. That's a variable. That's a number. Number, variable number. Number, variable number. And when you plug all that in, you are going to have an equation in x, y, and z. The coefficients of x is going to be that value. The coefficient of y is that value. The coefficient of z is that value. And then the constant that you could move over to that side is this product there. Because these are all minuses, you add them on the other side. That's how your line is typically going to look. So let's do it. Enough of talking about it, let's do it. Find an equation of the tangent plane to the hyperboloid z0 minus 2, z squared minus 2x squared minus 2y squared is equal to 12. Find an equation to the tangent plane to that hyperboloid. Okay. Now, just as a little bit of a refresher, that has to be a elliptic. Let's see, am I saying that right? It's a hyperboloid of, can we say how many sheets? It's not a hyperbolic paraboloid. This is a hyperboloid. Now, hyperboloids come either 1 sheets or 2 sheets. I don't know if you can really tell on this yet. Okay, and it really doesn't matter. But that's so don't.
You're going to get minus x and minus y, so you got a top end and a bottom end.
Yeah, yeah.
So that's what's going to happen. We're going to have this and that.
Yeah, I haven't figured it out yet to know that. I can't remember. Yeah, I think to be of 2 sheets, this would have to be a -1 over here, wouldn't it? I don't remember, but yeah, I shouldn't have even brought that up, but I've got to go back and review that.
Because look at those squares, you're going to come up
Yeah.
so if you move away from just those points there, you're going to come up with
Yeah, when x and y's are both zeros, you get z squared is equal to 12. So z is yeah, and so on 2 sheets, x and y both couldn't be 0. Then you would have a minus. So it would have to be a minus over there. Z squared would have to be a -12. So I think this is a 1 sheet. I'm pretty sure. And this is actually a circular because the x and the y's have the same coefficients. So anyway, so that's beside the point. Find the equation of the tangent plane to this hyperboloid at the point 1, -1, 4. Now, remember, I'm a skeptic, okay? A big skeptic. I don't want them having me do a problem that doesn't make sense, okay? So first thing I'm going to do is plug in and make sure this point is on this hyperboloid. Let's see if it is. Okay. This is the x. So this would be -2, -2, that would be -4, plus 16 equal 12. Yes, I feel much better about it now. It is on that shape, on that surface. So, what are we going to do first?
the partials
Of what?
partial of x,
Well-
partial of y, partial of z, and take the points.
Yeah.
Or just set it equals 0, which will just...
Yeah, to get it equal to 0, one of the first things you got to do is come up with your f of x, y, and z, which in this case is going to be z squared minus 2x squared minus 2y squared
minus 12, because that's equal to 0. Okay. Now, that doesn't mess with the partials at all. At all. Now, what I found a little, well, let's go on with it. Okay, so what are you going to do next? Take a partials. Okay, partial of f with respect to x at x, y, z is negative 4x. Partial of f with respect to y at x, y, z would be negative 4y. And partial of f with respect to z at x, y, and z is 2z. Okay. Now, what in the world do we do with those?
And then you get your point there. So you plug in, like for the x,
Okay.
for the partial of x, plug in your 1.
Okay. So we're going to do that and say the partial of f with respect to x at 1 minus 1, I can't write, 4, is negative 4. Partial of f with respect to y at 1, negative 1, 4, is 4. And the partial of f with respect to z at 1, negative 1, 4 is, it's what, 8? Is that what you said? Yeah, okay, I don't hear well. All right, you've done that. Okay?
And then, so it'll be your partial times, it's like the partial of x, which is negative 4,
Right?
times x minus
1.
1.
Yeah, okay. So that would be minus 4 times x. I can't write. That's not a 4. It looks an awful lot like a 4. Okay. That should be an x. Okay. X minus 1 plus 4 times
y minus
y plus 1 plus 8 times, yes, z. You get me off, okay? You did that on purpose, didn't you? Okay. Z minus 4 equals 0. Now that's not because f was 0 or anything like that. That's because the dot product of that is 0. And that's what we just did. Dot product of the vector, any old vector that goes through that point with components x, y, and z, not those points. Okay, so let's multiply this out. What does that give us? Yo! There we go. That's what I said. This, I think it has something to do with the power here. When it gets hot, it just tends to start fluctuating. So what do we have here? Negative 4x plus 4 plus 4y plus 4 plus 8z minus 32 equals 0. Okay? So let's sort of straighten this up a little bit and make it, I kind of like to go to the other side, which is what I want to do to begin with, but let's make this 4x minus 4y minus 8z. I'm moving all those over there, and this would then be plus, I kind of like to do it, let's just make it equal to a negative 24. Yeah. Now, that's just because I like to lead off with a positive number. It doesn't matter, okay? I don't think. Okay. That is the equation of the tangent plane. Equation of the tangent plane to that hyperboloid at that point. Now, let's make sure that this point is on this plane. It better be, hadn't it? So that would be 4 plus 4 is 8.
And 32.
Minus 32 is 24, is negative 24. Okay, yeah, that's there. A nice little check. It's not a very serious one, but it is a little check there. Okay?
Would you stop just a minute?
Now, what else can you do to that?
No, well, I'm just,
Yeah, what did you say?
I'm trying to go all the way back to two-dimension, and then, okay, like when we was doing the line, then you got the...
Right. Okay, but
All right.
did you say factor out? Did you? I thought I heard
No,
that.
I didn't say factor out.
Oh,
but
I'm
you
sorry.
can.
Yeah, let's do that. Divide everything by 4. And what you get? X minus Y minus 2Z negative 6, right. Let's see. Oh, they left it as a plus 6 equals 0. I don't care. X minus Y minus 2Z plus 6 equals 0. Okay. Now, to keep me from, oh, Bill, I think you're right. This must be of two sheets, because this parabola they show is way up there. So you're right. I was thinking it was one sheet, but it doesn't seem to be. Okay. Let's get their picture here. I think I'm going to have to erase this. Are y'all okay with doing that? Okay. All right, begin by writing the equation equals 0, which in my mind doesn't make a dab of difference because the partial of the other one would still be, okay. Then considering that to be your capital F, it makes a little difference because then this partial is equal to 0. And as we said, the partial of that with respect to x is minus 4x minus 4y and 2z. And at the point there, the partial derivatives are negative 4, positive 4, and 8, which we got. So an equation of the tangent plane must be negative 4 times x, blah, blah, blah. We multiply that through, and you get minus 32. I'm sorry, you get same thing we did, and that gives you that. Divide everything by a negative 4. Is another way to do it, is x minus y minus 2z plus 6 equals 0. Same thing we got. Here's what I didn't do. Thank you very much. And this shows it is a hyperboloid of 2 sheets, not 1. Okay? So I think I have my thinking backwards here. Here is a point. 1 on x, 1 on x, minus 1 on y, and up here at 4 on z. And you're down there at that lower part there, and you have a tangent plane to that, and this is taking off your x's and y's are similar in steepness, except the x is positive, y is negative, okay, at this point, okay, and the x, okay, this plane's going up like this. The x component is positive, y is going downward in the positive y direction, or upward in the negative y direction, and then your at this point z is going down, yeah, and you're increasing the other two z's going way down. Okay, so I think that looks like you're expecting. So this figure shows a portion of the hyperboloid, which must be of 2 sheets, and the tangent plane at that point. Okay. Now, that was example 2. Seems like they show this equation one more time, so let me show it one more time. Okay, now they're going back and doing, I think, almost what I was suggesting. To find the equation of a tangent plane at a point on the surface z is equal to f of xy, which is where we started a long time ago. You can define capital F as this, which we have done before. Then S is given, now I didn't do a thing to it, it's just blinking on its own. And I have no idea why. Okay. You can define the function this way, which is exactly how we did before. Then S is given by the level surface, that, which is what we were doing, and by theorem 1313, an equation of the tangent plane at S, or to S, at the point x0, y0, z0, is the partial of your little f with respect to x at x0, y0, times x minus x0. And if you think about it, the partial with respect to x, because remember, the other one wasn't given. Okay. This is one that z is equal to f of xy. The other one, I think I said it earlier about a different one, you couldn't come up with that because that would have been a z squared is equal to. And maybe that's where we got a upper and lower two sheets, because this is plus z and there's the minus z. So, yeah. But this is one that f of xy is z, okay, not z squared, okay. So that's the difference here, that you can do this. Then this breaks down to just that partial times x minus x0, this partial times y minus y0, and then the last one, the partial of this with respect to z is minus 1. So there's your minus, z minus z0. There is no partial there, it's minus 1. Okay? And that's equal to 0. And you're basically just about where we started then. Not quite, because you eliminate, oh, they don't do a thing with it.
Well, see,
Oh, they do.
I'm looking at like a step up. Remember you said you can't talk about a line in space because you have all these
A tangent line.
tangent lines.
Yeah, you can talk about them, but you have an infinite number of them.
Okay.
And that forms the plane.
That's why I was trying to put this back in 2 dimensions.
Oh, okay.
Because f of x is a tangent.
Right.
And then when we got y minus y0 is equal to the tangent of that line, and then times the point you're going to make up x minus the point you were given.
Yeah.
And that becomes the equation of the line.
Uh-huh.
That's what I was trying to put that in terms of.
Oh, I'm sorry. Yeah.
Try to understand what was going on.
Right. Okay. Do we need to go back a slide or two?
No, we
Oh, it's fine. Okay, good. All right. Now, okay. They said all that at the bottom of page 933 and then went to the next topic on page 935, skipping example 3, 4, and 5, which we would use this thing we just talked about here. So I've got to find some white space to work. I guess this is the best we're going to do. Let's see if we're going back a little bit further. Nope. That's about as good as we're going to get. Okay. Now, don't let me run over. Okay. We got plenty of time. Let's do example 3. Find an equation of the tangent plane. find an equation of the tangent plane to this paraboloid, which is z is equal to 1 minus 1/10 times x squared plus 4y squared at the point 1, 1, 1/2. Okay, and again, I'm a cynic, so let me make sure this point is on this plane. So when x equals 1, that's 1. Y is equal to 1, that's 4. 1 plus 4 is 5. 5/10 is 1/2. 1 minus 1/2 is 1/2. Yes, it is. Okay? That point is on this paraboloid. Okay. And it says find an equation of the tangent plane to this paraboloid at that point. Okay? So what we were just doing was let's do, now this can be your z is equal to little f, right? So let's do the partial of little f, and this part would be the same thing if we did capital F. It doesn't really matter which one we do, but since it's given in this with respect to x, what would that be? Negative x over 5, or 1/5 x. Partial of f with respect to y. Negative 4/5 y. Okay. And the partial of f with respect, well, z is f, so that, in a sense, well, it should be the capital F here is 1. Okay. Because, okay. And this can be capital F here and capital F here. Be the same thing, you know, if you put this, well, is it quite the same thing? Or would it be, is this be a -1 then? Yeah. Well, it's immaterial because it's just the coefficient for the z is 1, and it's always a -1. So without writing it that way.
Well, they use lowercase in the book.
What's that?
They use lowercase in the book.
Yeah, I know, and what I'm getting at is that we don't need to go to the uppercase, but we don't need to say f sub z either. We just leave it alone, okay? Because it is the derivative of z with respect to z, which is what f is 1. This is f. This is our little f. But it's our x and y. And the change of that with respect to z, well, it's itself. That's 1. So, when we write out the formula then, we need to plug in these values. F sub x at 1, 1, 1/2 would be negative 1/5. F sub y at 1, 1, 1/2 would be negative 4/5, and that's all we need. Okay. Now, with that in mind, it's minus 1/5 x minus 1, right? Okay. We're doing this. Whoops. Oh, wait. I'm in the wrong place. We're doing this, okay? F sub x of this times x minus 1. You know, this is 1, 1. And partial of this at that point, which is what we calculated at x this is just going to be minus 1 at times z minus 1. It's always a minus 1 if you pulled it to the other side. Okay, keep thinking I've got to go forward here, but I'm going back. Okay, so this will be 4/5 times y minus 1 minus z minus 1/2. Okay, and that's equal to 0. Always equal to 0 because it's the dot product of the two things perpendicular to each other. Okay, so what does that give us? Now, since that's equal to 0, why don't we just multiply everything by 10? Would that be okay? Because we've got 5s down here and 2s over there. Let's just multiply everything by 10, right? So 10 times this would be a minus 2x plus 2, right? Okay. Minus 8y plus, I shouldn't be doing all this, getting myself, it's 8, okay, and minus 10z plus 5, right, is equal to 0. I just like whole numbers better than fractions. Sorry, I know you love your fractions, but yeah. Okay. Okay. Now, I think I'm going to move all the variables to the other side just so I can get them positive, and that would be 2x plus 8y plus 10z equal, you said how much? 15. Okay, I'm sorry. I don't hear well. Okay, equal 15. Got it. Okay. That should be the equation of the tangent line to the paraboloid at that point. Again, cynic that I am, I want to make sure this point is on that line. Let's see. 2 plus 8, that would be 10, plus 1/2 of 10 is 5. Yep, that's 15. So I feel fairly good about it. Let's see what they got. Where are we? Here we are. Oh, they left it in fifths and halves. I don't know why. But if we had left it in fifths and halves, I don't know why we would have done that, but it would have worked out to this. Because what you can do is divide everything here by 10. And you get, x over 5 plus 4y over 5 plus z is equal to 3/2. And that's basically what they've got. They just have minuses rather than pluses, and they have the 3/2 on the same side. Okay.
Theirs looks worse.
What's that?
Theirs looks worse.
I think so. Okay, thank you very much. Very seldom does anyone say anything I write looks better than anything else. It must be bad. All right. The gradient produces a convenient way to find equations of normal lines. Okay. In example 4 can be seen at larsoncalculus.com, or at least an innovative, interactive version of this type of example can be seen there. All right, to erase? Yay? Okay. How are we doing? Okay, we've still got time. All right. Find a set of symmetric equations for the normal line to the surface xyz is equal to 12. Now, my first question to you is, do you remember what these symmetric equations are? Okay. They don't even give you the reference here, but it was back in, I'm pretty sure it was 11. Let me make sure of that. Yeah, okay. Maybe not. Maybe it was 10. Be far easier to just look it up in the index, wouldn't it? Yeah, I think it's 10. Let me look. Symmetric equations. Please be there. Symmetric equations 787. Okay, I was within a page or two of landing on it. Oh wait, 787. No, a few more pages than that. A section or two of it. Yeah, there it is. Lines and planes in space. There it is. And your symmetric equations look like x minus x1 over a equal y minus y1 over b equals z minus z1 over c. Those are your symmetric equations. And they basically tell you about a line in space. You can either express it in parametric equations or what they call symmetric equations, where you lose your parameter. Okay, so they want it in terms of the symmetric equations with no parameter in it. Right now I'm going to put a marker there so I can get back to it if we need it. Okay. At the point, so find the set of symmetric equations for the normal line to the surface at this point, 2, negative 2, negative 3. 2, negative 2, negative 3. And again, you know what I'm going to do. I want to make sure that point is on that curve. Well, 2 times negative 2 would be minus 4 times minus 3 is minus 12. Yes, it's there. Okay. Now, they like to get to your capital F, so let's do that first. Capital F of x, y, and z. Of course, here would be pretty simple.
We're doing
X, y, z minus 12 equals 0. The capital F is always equal to 0. So all you do is subtract. Okay. Now what do we do? Yeah, do the gradient of f, which are your partials, and that would be, well, let's just call it this. It's much less writing if you do the f sub x I plus f sub y j plus f sub z k. Okay? What is your f sub x? YZ, isn't it?
Yes.
YZI
Plus
XZJ
plus
XYK. Now, at this point, what's your YZ?
Negative 4.
YZ?
Oh, YZ, I'm sorry.
Yeah.
6.
6I
minus 6J.
minus 6J. Now you're
minus
4K. Okay. That's your gradient vector. I don't know if we needed all that. but that's what it would be there, 6i minus 6j minus 4k. Now, the normal line through this point, that's what we're looking for, the set of symmetric equations for the normal line at that surface, okay, at that thing, has direction numbers. These are what they call the direction numbers. 6, -6, and 4. Now, if you go back to your formulas before, that's your A, B, and C in your denominator. Those are direction numbers, okay? So, it's simply x minus 2, that's your thing, over 6 is equal to, you help me.
Y plus 2 -6.
Okay, -6, and that's equal to
Z plus 3.
over -4. Okay. Now, do they do a lot more for me? Not really. Okay. That's just, those are your direction numbers. And whatever line that is, that corresponds, has direction numbers, and the corresponding set of symmetric equations is that. Now, can I draw that for you necessarily? I don't know. I mean, it's a rather bizarre looking thing. What I would assume from it, and I may be wrong on this, that you have a very slight positive slope, 1/6 x, and offset by 1/3 from origin maybe, and a very slight negative slope for your y, and a very slight negative slope for the more, but you have still slight negative slope for your z. I mean,
That picture looks awful.
I know.
I don't know what you call that.
It's a three-dimensional hyperbola, I guess. But it doesn't even quite look right there. Yeah, it's awful. But that's what it is. It's curving away from each other in every dimension. And it's a mess. I'm glad I didn't have to draw it. Okay. But looking at those values, let's see if, I don't know if this will be any good or not. No, we're running out of time. Oh, man, this thing is heavy. Okay. Your x, when x is increasing, your gradient is also increasing. There's the gradient right there at 2, -2. So 6x, there is positive x is coming this way. So it's hard to say which way, but this is coming this way. Minus y is this way, that's -6y, and -6z is pretty obvious, that's going -6z. What's not easy to tell is you're coming out x really strongly here. It's just that you're going down and over even more strongly. And that's the point. At that point, 2 on x, -2 on y, and -2 on z. So you're way down there. And like you said, that's a middle graph. Okay. Now, so you got the symmetric equations. And again, to me, those symmetric equations don't really make me warm and fuzzy inside. All right, do we have time for example 5? I'm kind of thinking not. Though it looks like a fairly easy problem, I don't think we'll finish it in 4 minutes. Isn't that about what we got? Okay. So let's just go on and let me give you your homework exercises here. You can do either 3 or 5. They're both a Calc Chat. 5's a Calc View. You can do any of the, I would definitely do 7. It's a Calc Chat and Calc View. And then try to do some of the others, 9 through 15. They're only at Calc Chat. Any of the odds 17 to 25, they're all at Calc Chat. 19's at Calc View. Any of the odds 27 to 31, they're all at Calc Chat. 27's at Calc View. And let's stop right there, because the next is finding the angle of inclination. That's what we didn't get to yet. So let's look ahead for just a moment. We'll finish 13.7, and then 13.8, I think this is where Bill's been itching to get to. He finds his extrema of these shapes, these surfaces. So we'll do that. Is 13.8. And 13.9 is a great section, but I'm afraid we're just not going to have time for it. Definitely one to read through. We may just do a quick slideshow of it just to give you a flavor for it, so if you ever need to do it, you certainly can. This whole concept here is pretty much applied optimization problems. And I know Bill's just here for the fun of it. Are you going into engineering? Which one? Mechanical. Okay. You may at some point need something like this, but it's optimization stuff I always think of more as like industrial engineering. Like trying to optimize use of equipment, manpower, labor, blah, 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 capital and stuff like this, and come up with the optimum output for your given input. And so that, I think, is what this is. Since none of you are that, we'll just do it quick and dirty on that one. I won't test you on it. It's a very short section, so it won't take long just to do that. 13.10 is Lagrange multipliers. That's more optimization. Those are techniques and stuff. I wish we had time for them, but you know, Lagrange is certainly a decent paper topic if you're interested. Or how did he develop these Lagrange multipliers? Or who in the world uses these Lagrange multiplier? How are they used? That kind of stuff. Again, these are what they call constrained optimization problems. Okay, and 1 constraint, 2 constraints. Very much in my mind, what you want to call it, industrial engineering type. You may have it in mechanical too, when you're trying to, if you're looking at different thicknesses of metal or dimensions. Say again, what were you thinking, Bill?
I would say you're going to see it mechanical, because they're going to try to do maximum resources.
Right.
As to the profit we want to make over here.
Mm-hmm. And guess what? Once you become an engineer, you could wind up doing just about anything. My older brother's roommate at Georgia Tech was a mechanical engineer. He wound up basically running, I think it was a Frito-Lay plant. Okay, he was doing mechanical, he was doing industrial, he was doing, I mean, so they're going to use you wherever they need you because you know how to think. So by the time you finish engineering, so anyway. Yeah, you're probably right. You might need it too. I wish we had more time to do it. But you see, we've still got multiple integration coming up, which is another 8-section chapter. And then we're going to try to get to chapter 15. Whether we make it or not, I'm not certain. But chapter 15 is then your what they call vector analysis, vector fields. You talk about all these things like line integrals, Green's theorem, parametric surfaces, surface integrals, divergence integrals, Stokes integrals. Again, another 8-section chapter. We're not going to finish that one. I don't know if we'll even get to it, but we need to pound on as fast as we can. So we'll just do a slideshow on the next 2 sections once we finish the one we're on now. No, I'm sorry. We do 13.8 and then slideshow on 13.9 and 10. All right, any question? That probably ate just about all the rest of the time, didn't it?
Yep.
All right, so well, first let me stop this.